Hello, my name is Roberta, and today I'll be talking about an Alexander method for infinite type surfaces. But first, I would like to thank the organizing committee for tech topology for giving me the chance to speak. All right, so let's begin with an example that we're all familiar with, hopefully, and it's linear maps on vector spaces. So a linear map on a vector space is completely determined by how it acts on a set of basis vectors for the vector space. Similarly, a set of isotopic classes of homeomorphisms on a surface is determined by how it acts on a special set of curves on our surface. This is the essence of the Alexander method. So the Alexander method states that if we have a homeomorphism phi of a surface, it is determined up to isotopy by how it acts on a nice set of curves. So we're going to call such a nice set of curves gamma, and I might also refer to it as an Alexander system. So a lot of work has gone into this, beginning with finite type surfaces, where the Alexander method was proven by Dane, Thurston, Farr-Margolite, and more recently, it has been proven for families of nice systems of curves on infinite type surfaces by Hernandez, Morales, Valdez, and Hernandez-Hidber. All right, so let's take a look at a theorem by seeing an example. Let's take the surface to be a punctured plane with these punctures just marching off to infinity on the right. And our Alexander system to be gamma. So all of these arcs actually that connect our punctures. All we need now is a homeomorphism, and we have one. And this homeomorphism, what it does is it takes each curve in our original system and sends it to another curve colored here. And they're all, each curve in the image is isotopic to some curve in the original system. And something that we can notice is that it kind of looks like this homeomorphism flips the plane upside down up to isotopy. But all we know is how it acts on these curves. What the Alexander method states is that if we actually know everything about phi, it is the hyperelliptic involution. It is the mapping class that flips the plane upside down because the mapping class is completely determined by how phi acts on the curves. That being said, let's take a look at a few applications of the Alexander method. So the first application is that we can verify relations in the mapping class group. And the way that we do this is basically we draw a picture. A bit more work goes into it, but the main thing we need to do is we want to take our surface, we want to take an Alexander system on the surface, and we follow how this Alexander system is acted on by our homeomorphism. We know that this is provable using past results, especially those of Hernandez, Morales, Valdez. A second application is that we can show that the centralizers of certain twist subgroups of the mapping class group are trivial. So if we take our Alexander system to be gamma, and then we take a subgroup of the mapping class group generated by, let's say, the 100th, doesn't matter which as long as it's non-trivial, twist about each curve in gamma, then the centralizer is trivial. The reason behind this is because anything that commutes with all of these twists must actually fix the curves that are being twisted about. And if you fix all the curves in our Alexander system, you have to be isotopic to the identity. A perk of the Alexander method is actually that we can develop tools to tell whether a system is nice in this way. And this application kind of allows you to do that. A third application is that we have a simpler basis for the topology of the mapping class group, wherein open sets about the identity fix the first n curves in gamma. Thank you so much for taking the time to listen to my talk, and I hope I will see you later at the conference.